Hello everyone, thank you so much for giving me the opportunity to give this talk today. Today I'd like to talk about cosmological probe combination for current and future surveys. Now before I start, I'd like to say that even though it's me giving this talk today, the work that I'm going to present is the work of many fantastic people, and a subset of those is shown here on this slide. And I'd like to particularly highlight the fantastic junior scientists with whom I have the pleasure of working with: Ruhi, Leah, Michael, Alex, and Robert. Now, the last 3 decades have seen an immense progress in observational cosmology, which has led to the establishment of the lambda cold dark matter cosmological model. This model fits most of our observational data really well, and this is quite remarkable given the range in length scales and time scales covered by current observations. What is even more remarkable is the fact that lambda CDM is pretty simple and it relies on 5 key pillars: the standard model of particle physics, general relativity as the theory of gravity, inflation as a mechanism to generate primordial perturbations, and the existence of 2 dark components, dark matter and dark energy. Now, despite its simplicity and observational successes, little is actually known about some of these key ingredients. In lambda CDM, dark matter and dark energy make up approximately 95% of the universe's energy density content, but dark matter has not yet been directly detected in the laboratory, and we're really far away from understanding what dark energy might be. General relativity is only now starting to be stress tested on cosmological scales, and inflation involves energies that we cannot reproduce in the laboratory. And so one of the key goals of observational cosmology today is to further constrain the properties of these key ingredients. Now, in order to do that, we need to move to the cosmological laboratory, which is our universe. And in order to learn about our universe, we can look at the so-called cosmological probes, which show us the properties of the universe at different moments in its formation history. Our earliest picture of the universe is given to us by the cosmic microwave background, whereas 2 complementary probes, galaxy clustering and weak lensing, allow us to probe the universe at much later times in its formation history. Now, in the following, I would like to very briefly go through these 3 cosmological probes in a little bit more detail, because these are the probes that are going to be most important for everything that I'm going to be talking about afterwards. So the cosmic microwave background is the relic radiation from the Big Bang, and it shows us a baby picture of the universe as it looked like when photons last scattered with electrons approximately 380,000 years after the Big Bang. Now, since this last scattering event is a precise moment in time, this means that the CMB is inherently 2-dimensional. Now, we can obtain cosmological information from the CMB by measuring its statistical properties. And in order to do that, what we do is we basically measure the correlation of the CMB temperature in different patches of the sky as a function of their angular separation. Now, we can either do this in real space, which gives rise to the correlation function C of theta, or we can also do it in Fourier space, which gives rise to the spherical harmonic power spectrum C sub L. Now, another really important cosmological probe is galaxy clustering. Now, galaxies are a biased tracer of the matter distribution in the universe, and the idea is that by measuring the galaxy clustering properties, we can learn about the statistical properties of the underlying dark matter distribution. Now, in order to do that, we do exactly the same thing as for the CMB, with one key difference, which is that the galaxy distribution is inherently 3-dimensional. So we either measure the galaxy clustering properties in full 3D, or we take the galaxy distribution, slice it along the redshift direction, produce a set of 2-dimensional maps, measure the angular galaxy clustering properties in all of these maps, and then reconstruct the 3D information by jointly analyzing the information in all of these maps. Now, this latter approach is called a tomographic analysis, and this is what I'm going to be talking about whenever I'm going to be talking about galaxy clustering in this talk. Now, finally, the last cosmological probe that I would like to touch upon is weak gravitational lensing. Now, gravitational lensing occurs because photons get deflected as they travel through space-time that has been curved by the gravitational lensing effect of the intervening large-scale structure. And what this means is that if we now go out and look at the images of distant galaxies, we're not going to see them how they intrinsically look like, but we're going to see them slightly distorted. In weak gravitational lensing, what one is trying to measure are the tiny but coherent distortions of galaxy images caused by the cumulative lensing effect of the large-scale structure between the distant galaxies and us. And the idea is that if we can measure the statistical properties of these distortions, we can learn about the statistical properties of the intervening matter distribution, and here both the luminous as well as the dark matter. And in order to do that, we do exactly the same thing as before, and we basically measure the correlations between galaxy shapes as a function of their angular separation. Now, all of these cosmological probes by themselves are super exciting. But what is even more exciting is that all of these cosmological probes are actually not separate, because they're all part of our universe that we can only observe through the photons that reach our telescopes here on Earth. And what this means is that any cosmological probes are actually correlated to one another. And as an example, you can think about a CMB photon traveling from the last scattering surface towards us. This photon is going to be deflected by the gravitational potential perturbations caused by the intervening large-scale structure, which means that the observed CMB temperature and isotropies are going to be correlated to any tracer of the large-scale structure, such as galaxy clustering or weak gravitational lensing. And these types of cross-correlations actually exist between any two cosmological probes. Now, no matter the cosmological probe we care about, if we want to obtain cosmological information from these probes, what we do is we basically go out, we measure our statistic of interest, which here is basically the galaxy clustering power spectrum. We compare it to theoretical predictions and then obtain constraints on the parameters of our cosmological model, which parameterize its energy density content, the properties of fluctuations, or also the properties of dark energy through its equation of state parameter. Now, different cosmological probes actually depend on different combinations of these cosmological parameters. And what this means is that combining cosmological probes is a really powerful way to further constrain our cosmological model, because it allows us to basically break parameter degeneracies that we would have in single probe analyses only. And this is nicely illustrated here in this plot, which comes from a recent work by Alex. This plot here shows the constraints on two key cosmological parameters, omega m and sigma 8, where sigma 8 essentially quantifies the clumpiness of the matter distribution in the universe. And here you can see the constraints on these two parameters for three different cosmological probes: for galaxy clustering and weak lensing alone, from CMB alone, and also from the combination. As you can see, basically the constraints that we obtain by combining all of these probes together are significantly tighter than the single probe constraints themselves, which is really due to this degeneracy breaking that we have when combining cosmological probes together. Now, apart from giving us tighter constraints on cosmological parameters, joint analyses have a number of different additional advantages, which are due to the fact that cross-correlations between different probes actually carry a wealth of information. First of all, cross-correlations really allow us to test the consistency between different physical tracers and therefore devise robust tests of our cosmological model. In addition, cross-correlations allow us to obtain constraints on astrophysical systematics, and they also allow us to cross-calibrate different cosmological probes against one another. And finally, cross-correlations also help us identify systematics that will be really difficult to find if we only had access to the autocorrelations. And all of these points are particularly important in the light of imminent surveys, which are going to be limited by systematic rather than statistical uncertainties. Now, as everything else, combining cosmological probes comes with its own set of challenges. First of all, as we combine an increasing number of different cosmological probes, we will end up with a very large data vector and a correspondingly large covariance matrix. In addition, all of these probes, come with their own set of nuisance parameters. And so if we want to obtain cosmological constraints in a joint analysis of many different cosmological probes, we will end up with a very very large parameter space. And finally, different cosmological probes can possibly also exhibit tensions between one another, which then raises the question if we are actually allowed to combine these two probes together. And this last point is illustrated here on this plot, which shows the constraints on the so-called S8 parameter for a number of different cosmological analyses. And S8 is really the cosmological parameter that is most tightly constrained by weak lensing, and is a combination of omega m and sigma 8, and it really measures the clumpiness of the matter distribution in the universe. And in the last couple of years, many different cosmological analyses have found that the measurements of sigma 8 from the CMB systematically differ from those from low redshift probes, such as, for example, weak lensing and galaxy clustering. And this, systematic discrepancy has been known as the S8 tension. Now, in the following, I would like to present to you a very recent combined probe analysis that we've performed in a work led by Alex, and I would like to particularly highlight how we have dealt with these three key challenges. And so our framework for combining cosmological probes is shown here on this slide. And this framework allows us to self-consistently combine cosmological probes at the power spectrum level. Now, in order to be robust to systematic uncertainties, we restrict our analysis to large scales for all of the probes that we consider, and we also use a simulation-based covariance matrix. Now, in order to be able to obtain cosmological constraints for the large parameter space that we have in our analysis in a reasonable amount of time, we use emulators for theoretical predictions, and we write all likelihoods in JAX. Now, in principle, this means that this allows us to really use gradient-based sampling algorithms, such as, for example, Hamiltonian Monte Carlo. But in practice, actually, we find that this is not really needed for our analysis, because the combination of GPU acceleration and just-in-time compilation that we can have with JAX allows us to obtain cosmological parameter constraints for all of our data in approximately 10 minutes. And so let us now look at the data that we use in our analysis, and we essentially subdivide our data in three different parts: CMB, LOSI, and BAO. On the CMB side, we use two different data releases from Planck and the Planck-independent CMB measurements from ACT and WMAP. On the LOSI side, we use CMB lensing and integrated Sachs-Wolf effect from Planck, weak lensing from KIDS 1000, and galaxy clustering from BOSS DR12. And finally, we also combine with baryonic acoustic oscillation from DESI DR1. And here on the bottom, you can basically see the sky fraction of all of the data that we've combined in our analysis. Now, before we can actually go ahead and combine all of these data, we need to assess the consistency between all of them. And the main concern here is really the consistency between CMB and LOSI in the light of the S8 tension that we've discussed before. And so what we do is we basically assess the consistency between the CMB and our LOSI data vector on S8 in two different ways. First, we look at a 1D tension metric, which basically measures the discrepancy in the marginalized 1D constraints on S8. And we also use a full parameter space tension metric, which essentially measures the probability of obtaining parameter shifts as large as the ones that we've obtained in our data. And let us just look at our fiducial case, which is basically the consistency between Planck PR4, so the latest Planck analysis, and our LOSI data vector within lambda CDM. And what you can see is that basically in S8, we see a tension which is a little bit larger than 2 sigma, whereas if we look at the full parameter space, this tension is reduced to a level below 2 sigma. And what this means for us is that we are confident that we can proceed to very cautiously combine these two data sets together, but always making sure that they are robust to, different analysis choices. And so now that we have reassured ourselves that we can actually combine our data, let us actually look at our cosmological parameter constraints, and let us first focus on lambda CDM. So here on this plot, you can see the constraints on sigma 8, omega m, h, and S8 that we've obtained from the data combination that we've seen before. First, you can see that the three CMB datasets that we've looked at in our analysis are very nicely consistent with one another, and you can also see that, as expected, they give a larger value of S8 than what we've obtained, what we obtain from the low Z data vector. If we now combine everything together, you can see that S8 gets pushed higher than what we would get from low Z, which is as expected, but you can also see that the constraints on all of the other cosmological parameters of lambda CDM are significantly tightened. And in particular, this analysis really gives us a strong constraint on S8, which we find to be robust to many different analysis choices, in particular also to changes in which kind of CMB data vector that we actually use. Now, moving beyond lambda CDM, we can also look at extended cosmological model. And here, one particular focus in our analysis has been to use our data combination to put constraints on the sum of neutrino masses. And here you can see the 1D marginalized constraints on the sum of neutrino masses from the CMB alone, and then also from the data what happens when we add our low Z data vector to it. And as you can see, basically adding low Z and then adding BAOs as well significantly tightens the upper limit on the sum of neutrino masses that we will get from CMB alone, and gives pretty tight constraints on this very interesting cosmological parameter. Okay, so what we've seen so far is that, combining cosmological probes is really quite powerful, in particular if we want to understand systematics and look at models beyond lambda CDM. But everything we have talked about so far has focused on large-scale power spectra. Now, what this means is, this means that we take cosmological fields, we smooth them, we throw away all of the information contained in small scales and non-Gaussian features. Now, we know that there is significant amount of cosmological information in cosmic fields at small scales and their non-Gaussian features. And if we really want to, deliver on the promise of future data to constrain fundamental physics, we need to take more of this information into account. And just to show you how dire the situation is, here you can basically see a galaxy clustering power spectrum that we've obtained in a tomographic galaxy clustering analysis of hypersubprime CAM data. On the x-axis, you can see the angular multiple L, which is nothing else than inverse angular scale. So the larger L, the smaller the scale we're actually looking at. And on the y-axis, you can see the spherical harmonic power spectrum. Now, looking only at large scales in this analysis would mean throwing away all of the data in the shaded region, which, as you can see, actually dominates our signal to noise. And so in order to overcome this highly unsatisfactory situation, we have very recently been working on several different analyses or ways to use more of this cosmological information in joint probe analyses. And I would like to give you 3 different examples. One on galaxy clustering, one on galaxy clusters, and one on weak gravitational lensing. So the main systematics, if we want to use galaxy clustering at small scales, is galaxy bias, which is the complex relation between the galaxy distribution and the underlying dark matter distribution. At small scales, this relation becomes increasingly complex, nonlinear, and very difficult to model theoretically. And so in order to address this challenge, within LSST desk, we have recently completed the so-called galaxy bias challenge, where we've compared several different galaxy bias models in the light of LSST year 10 data. And what we found is that basically hybrid galaxy bias models, which combine cosmological simulations and perturbative approaches, actually allow us to obtain unbiased constraints on cosmological parameters up to a Kmax of approximately 0.4, even for LSST year 10 precision, which makes them very promising to be applied to both current and future data. Now, another way to obtain more cosmological information from galaxy clustering is to move beyond 2 points. 2-point functions. Now, what is the next step after 2-point functions is essentially 3-point functions or its Fourier space counterpart, the bispectrum. And very recently, with collaborators in a work led by Lea, we have developed a novel estimator for the galaxy clustering bispectrum, for galaxy clustering bispectrum. And the idea of this estimator is that it's essentially a power spectrum of a squared field with a non-squared field, and it therefore shares many properties with power spectrum estimators. And what we found is that this estimator is actually unbiased, even in the presence of very complex survey masks, which makes it very promising to be applied to both current and future data. Now, another very powerful probe of the non-Gaussian universe are galaxy clusters. Now, galaxy clusters are the most massive gravitationally bound structures in the universe, and their number density as a function of mass and redshift significantly depends on the amplitude of matter fluctuations in the universe, and therefore omega m and sigma 8. And this is illustrated here on this plot, which shows the distribution of galaxy clusters, which obviously are these red yellow circles, for two different cosmological models as a function of redshift. On top, you can see lambda CDM, and on the bottom, you can see a matter-dominated universe. And as you can see, basically the number density of these clusters significantly differs in these two cosmological models. Now, galaxy clusters can be seen at many different wavelengths and can therefore be detected using several different methods. We can detect galaxy clusters in the optical by looking for large overdensities in red galaxies. Galaxy clusters also contain a lot of hot X-ray emitting gas, and so we can look for galaxy clusters in the X-ray. And finally, we can also use the CMB as a backlight to detect galaxy clusters through the so-called Tarmosunyaev-Seldovich effect. And the idea here is that basically, as a CMB photon traverses a galaxy cluster, it can undergo inverse Compton scattering with the hot ionized electrons in cluster cores. This gives an energy boost to the photon, which leads to a spectral distortion in the CMB, which we can then use to detect galaxy clusters from CMB maps. Now, common to all of these approaches is that they are not directly sensitive to cluster mass, which is what we need if we want to do cosmology with clusters, but to so-called mass proxies. And so one of the key systematics in galaxy cluster analyses is basically the relation between the mass and the observable. And one way to do that to calibrate this relation is to use with gravitational lensing. And very recently, with collaborators, we have developed a novel way to self-consistently combine TSZ-selected galaxy clusters with gravitational lensing. And amongst others, this allows us to self-consistently perform mass calibration and cosmological inference, which is absolutely crucial if we want to robustly marginalize over our uncertainties. And as you can see here, this method is also very promising to constrain cosmological parameters, as you can see from these forecasts for a joint analysis of SO and LSST. Now, finally, another very powerful way to constrain the small scale matter distribution in the universe is cosmic shear. As we've seen before, weak gravitational lensing and cosmic shear is sensitive to all the matter in the universe and is therefore completely immune to galaxy bias uncertainties. The last couple of years have seen 3 main cosmic shear surveys, which are now either completed or analyzing basically their last data releases. These are the Dark Energy Survey, the Kilodegree Survey, and the Hypersuprancam Survey. And here I'd like to focus a little bit on HSC, which is the survey I have mostly been involved in. So HSC is an optical survey that imaged approximately 1000 square degrees in the sky in 5 optical bands, G, R, I, Z, and Y, and it was completed in 2022. And HSC is very deep and has very good seeing, which makes it the stage 3 cosmic shear survey that most closely resembles stage 4 data from LSST. Now, within HSC, we have performed a cosmic shear power spectrum analysis with the year 3 dataset in an analysis that has been led by Ruhi, and you can see the cosmic shear power spectra from our analysis here on this slide. On the diagonal, you can see the autocorrelations for the 4 different redshift bins that we've used, and on the off diagonal, you can see the cross correlations. On the right, you can also see our corresponding constraint on S8. Now, despite me telling you a couple of minutes ago that cosmic shear is a really good way to constrain small-scale matter perturbations, our analysis has solely focused on large scales, which you can see here basically from the fact that all of the data in the gray regions has not been used in our analysis. And the thing is that theoretical models of cosmic shear at small scales are highly uncertain. And these uncertainties, as you can see, limit current cosmic shear analyses and will be even more limiting for future surveys, which will achieve very high signal to noise in this regime. And the thing is that even though cosmic shear is basically sensitive to all the matter distribution in the universe, the matter distribution at small scales is significantly affected by baryonic processes such as feedback due to AGN and supernovae. And these processes have the potential to suppress the matter power spectrum at small scales by several tens of %. Now, in order to learn about baryonic feedback, we can use hydrodynamical simulations, but there are 2 key challenges with this. First, hydrodynamical simulations are really expensive to run. And secondly, these simulations need to cover a vast range of scales, which means that they don't have the resolution to resolve the small scales at which these baryonic effects actually act. And so these effects are used into these simulations using subgrid models. And depending on the subgrid model, different hydrodynamical simulations make different predictions for the matter power spectrum suppression due to baryons. And this is illustrated here on this plot, which shows the matter power spectrum suppression as a function of wave vector k for a library of different hydrodynamical simulations. And you can see that basically, depending on the simulation and thus the subgrid model, the predictions for the effects of baryons are quite different. And what this really means, is that if we want to use cosmic shear at small scales, we need to basically learn more about baryonic effects on the matter power spectrum. And there are 2 main aspects to this. First, we need to develop flexible models that allow us to robustly marginalize over our systematic uncertainties. And secondly, we need to use observations of the baryon distribution in the universe to inform these theoretical models, as well as hydrodynamical simulations. And one way to model baryonic feedback in an efficient way is the so-called baryonification model. And the main idea of baryonification is to use n-body simulations and displace particles in these simulations according to analytic density profiles in order to mimic the effects of baryons. And this method has been shown to match the results from a library of different hydrodynamical simulations, but very recently with collaborators, we have basically revisited this model and worked on improving it in order to reach the accuracy needed for stage 4 surveys. And some of our results are shown here on this slide. So this plot here shows the comparison of the gas density and gas pressure profiles as measured from the Flamingo suite of hydrodynamical simulations to the fits obtained from baryonification for 5 different halo mass spins, spanning masses from 10 to the 12.5 to 10 to the 15 solar masses, and for 3 different redshifts, 0, 0.5, and 1. And as you can see from this pretty busy plot, is that the fits from baronification actually match the hydrodynamical simulations for all scales, redshifts, and mass bins used in our analysis. And this, like consistency with hydrodynamical simulations makes this model very promising to model and learn about baronic feedback, both for current surveys, but also in light of future surveys such as LSST and Euclid. And so the question now is, how do we use this model to learn about baronic feedback? Or in other words, how do we actually probe the baryon distribution in the universe? And there's many different ways to probe baryons in the universe. We can basically probe baryons through their X-ray emission. We can again use the CMB as a backlight to probe the baryon distribution in the universe through the Zunyaev-Seldovich effect, where we have the thermo-Zunyaev-Seldovich effect, which is exactly the same as what we use to detect galaxy clusters. And we also have the kinematic Zunyaev-Seldovich effect, which is due to scattering of CMB photons with electrons with a non-zero bulk velocity. And finally, a very novel and potentially promising probe of baryonic feedback are fast radio bursts. And in the following, I would like to give you two different examples of how we use baryonification to learn about baryonic feedback. The first one will be on combining X-ray and KSZ data, whereas the second one will be on fast radio bursts. And so in a very recent analysis that has been led by Michael, we have basically used baryonification to jointly fit KSC measurements from the Atacama Cosmology telescopes and X-ray gas fractions from eROSITA. Now, the KSC measurements are essentially sensitive to the gas distribution around galaxy groups and clusters, whereas gas fractions are essentially a measure for how much gas has been expelled out of halos as a function of their mass. And as you can see, basically the fits from baryonification that have been obtained by jointly fitting both of these two data sets actually do a pretty good job at jointly reproducing both the KSZ measurements and the X-ray gas fractions. Now, in order to learn about baryonic feedback, we can now use these results and look at what they predict for the matter power spectrum suppression. And this is shown here on this slide, which shows the matter power spectrum suppression as a function of wave vector k for basically a wave vector k as predicted basically by the combination of KSZ and X-rays. And as you can see, these two data sets actually predict a pretty strong suppression of the matter power spectrum, which is significantly stronger than what we would expect from the fiducial Flamingo hydrodynamical simulation. But it matches very well with the high feedback version of Flamingo, as you can see in this plot. And this is very nicely consistent with other recent analyses, and it will be really interesting to see how this compares to current and future weak lensing analyses as well. Now, as we've said before, another promising probe of the baryon distribution in the universe are fast radio bursts. Now, for me as a cosmologist, fast radio bursts are short, luminous radio pulses whose different frequency components arrive at our telescopes slightly delayed. And these dispersions are due to interactions of these radio pulses with ionized electrons along the line of sight and are essentially quantified through the so-called dispersion measure. And the dispersion measure, dm, is nothing else than the integrated electron density along the line of sight, and it receives three main contributions. First, from the host halo where the FRB sits in, then from the large-scale structure between the FRB and us, and finally from our Milky Way as well. Now, very recently with Robert, we have used baryonification to model the host halo contribution to the observed FRB DM. And we found the PDF of the host halo DM to strongly depend on baryonic properties of the host halo, and comparing to hydrodynamical simulations, we found that our really simple analytic model allows us to reproduce both the host halo DM and the matter power spectrum suppression as observed in these hydrodynamical simulations. And this is really promising if we want to use this model to actually model the host halo DM, but also if we want to, use this novel observable as a testbed for baryonic feedback at some point. Now, everything that we've talked about so far has mainly focused on 2-point or either 3-point function information. And the question now is, is this everything? Is this all the information that we can extract? And also, a related question is, as we move towards more complex statistics, how do we make sure that our results are actually robust to systematic uncertainties? So naively, what you can think about doing is to basically take a very complex cosmic field, extract an increasing number of increasingly complex features, and then perform inference in a joint analysis of all of these features. Now, this immediately raises two different questions. First, which features do we pick and where do we stop? And secondly, as we pick an increasing number of increasingly complex features, it basically becomes impossible to write down a likelihood for the data. And this is a big problem because if we cannot write down a likelihood, we cannot perform Bayesian inference, and so we cannot obtain constraints on cosmological parameters. Now, fortunately, several different methods have been developed that allow us to perform inference without having to explicitly write down a likelihood. And these go under the name of simulation-based inference. And simulation-based inference really relies on our ability to create forward models of our data, which are synthetic copies that resemble our data vector as closely as possible. And the main idea of simulation-based inference is to basically use an ensemble of these forward models to learn the posterior of our model parameters given the observed data. And these methods have several different advantages compared to traditional methods, which are particularly important in the light of future data. First, forward models in principle allow us to retain all of the information contained in cosmic fields, which is as compared to, for example, which is not the case if we use a likelihood-based analysis, which only focuses on the power spectrum. And secondly, forward models facilitate the inclusion of systematic uncertainties, as it is usually much easier to forward model systematics than it is to actually write down an analytic model for them. And this is particularly important in the light of combined probe analyses, which very often feature complex, potentially correlated systematics. Now, what this really means is that as we move, away from likelihood-based approaches towards simulation-based inference approaches, the most important part of our analysis will be the creation of these forward models. And these forward models need to include a model of both the physical process that we are interested in, but also of the measurement process itself. And as you can imagine, these will become pretty complex pretty quickly. And so if we want to use simulation-based inference for cosmology, we need to be able to limit the number of forward models that we need for inference, as well as the runtime that we need to generate one of these forward models. And this is particularly important if we want to use simulation-based inference for combined probe analyses. And so with Michael, we have very recently started on using simulation-based inference to jointly analyze TSZ-selected galaxy clusters and regravitational lensing. And Michael is currently working on using baryonification to jointly model TSZ-selected galaxy clusters and relensing in an efficient way, which will then allow him to basically very quickly generate a large number of correlated realizations of these two probes and then perform simulation-based inference with this. Now, starting to work on these, analysis methods is absolutely crucial because the cosmological data revolution is upon us. Euclid and SO are already taking data, and LSST will start taking data very, very soon. And these surveys will be followed by other high-precision surveys in a couple of years as well. And all of these surveys by themselves will be absolutely transformational for cosmology, but what will be even more transformational will be their combination. So in order to ensure that this promise is really met, we need to move beyond traditional methods, using methods such as the ones that I've talked about in this talk. And I'm very hopeful that with this, we will be able to uncover some of the mysteries that the universe is still holding out for us. This already brings me to the end of my talk. In this talk, we've seen that combining cosmological probes is really a powerful way to constrain our cosmological model because it allows us to break parameter degeneracies, it allows us to perform robust tests of our cosmological model, and it helps us to identify, understand, and calibrate systematic uncertainties. We've also seen that future surveys will deliver high precision data, which means that a significant information will be contained in small scales and non-Gaussian features, but also means that these surveys will be limited by systematic rather than statistical uncertainties. And this completely new regime in cosmology really requires the development of novel analysis methods that are built on the complementarity of different cosmological probes. And I've shown you some of our approaches to develop joint probe analysis methods to take more of this information into account. That's it from me. Thank you very much for listening.